If you're new to the channel, my name is Matt, and in this video we are going to go over a thorough, comprehensive understanding of the operation and how to test a MAF sensor. There are different types of them, of course, and also how to use the MAF sensor in a diagnosis. When we understand how it works, we can take advantage of that. And for those of you 2%ers that have been with the channel, you know what's coming up. We're going to go to the dry erase board of knowledge, get a thorough understanding of the background, and then apply those concepts to an actual vehicle, two vehicles in this case. So let's get started. All right, so our goals for this video, we are going to, of course, get a strong fundamental understanding of the theory of operation with several types of MAF sensors, actually, how to test them and everything like that. Of course, apply those applications onto actual vehicles in the second part of the video. And then in the third part, we are going to sort of put together the MAF sensor with the other air induction components and fuel monitoring systems, because nothing is an island in the car. It's important to understand how everything works together in order to make proper diagnosis and prevent misdiagnosis, more importantly. And also we'll talk about some other things with the MAF engine versus the MAP only engine and performance differences, different factors to consider with that, and the effects on vacuum leaks, all that. So a little bit longer video than normal with this series, but we're not just doing this sensor, we're tying everything together. So let's get started on some basic understanding of what a MAF is. As you guys are well aware, artistic ability has never been my strong suit. But what we've got here is a diagram with pretty much all of the air induction components that you would find on most typical engines. A little bit busy here, but the thing is, we have covered all of these except for the MAF sensor in other videos, and I will put a link to all of those other videos in the description. But the thing is that I'm going to highly recommend that you watch those other videos before this one, because this video is going to be different. We're not going to specifically talk about the MAF sensor alone. We will, of course, do a little bit of that, but also we want to tie in with how it interacts with these other things. If you don't know what they are, then that's difficult to do. It is also integral that if you are going to make diagnoses on or using a MAF sensor, that you understand fuel trim. And I have a video on that, which in my opinion is the best video on this channel, and actually I think the best video on the internet on understanding fuel trim. So if you're going to be an advanced diagnostician, you've got a lot of homework to do. There's no easy way around it. But let's go over what we have here. So we've got our engine here with, of course, our throttle, and we've got an exhaust. Air, of course, comes into the engine. As you guys have seen me say almost ad nauseum, some of you make fun of me for it, but the engine is always going to try to maintain, well, not always, but pretty much always, and that is the engine's obsessive compulsive desire to maintain a stoichiometric ratio, yes, I said it again, of 14.7 parts air to 1 part fuel. In order for an engine to do this, it is essential that it knows how much air is coming to the engine, and then it adjusts the fuel delivery by lengthening or shortening the injector pulse length to match the fuel delivery that would result in that final ratio. So for a brief review, the air comes in, the temperature of the air measured by the IAT, or intake air temperature sensor, goes through the MAF, which of course we will describe its operation in this video quite extensively. When the air comes past the throttle position is noted by the engine computer. All of these in blue connect to the engine computer. So the engine computer knows how open the throttle is through the throttle position sensor. There is also idle air control, which also helps to monitor the amount of air coming in. It allows for a bypass of air to control idle. It is actually the only method that the engine uses to control air induction. Everything else is air coming in, and the engine uses fuel to adjust this mixture, whereas with idle air control, that's the only PCM control for air intake into the engine. Of course, you've got your cylinder, your fuel, and the air, mix in the cylinder, combust, and of course that exhaust is validated by the O2 sensor, or in some cases the air-fuel ratio sensor in newer cars, to look at the amount of oxygen present in the exhaust and also hydrocarbon and determine if this mixture went accordingly. If the oxygen sensor determines that there is a lean response, then it is going to call for the addition of fuel through fuel trim, which we talk about in the video, to increase the fuel delivery to bring up to that 14.7 ratio and return your stoichiometric. If the O2 sensor detects rich, it will cut back fuel injector pulse length and fuel delivery to lower the fuel part of this ratio to bring it to 14.7 to 1. The whole point of the entire operation is to maintain stoichiometry so the oxygen sensor behavior is reported accurately, or air fuel sensor, which I also have a video on, by the way. Okay, and if I went through that pretty quickly, all of that is explained in much better detail with the fuel trims video. But what we are going to do now is focus right in on the MAF sensor, because you guys should be familiar with all these other components from the other videos. And we are going to talk about how the MAF sensor works. So focusing in on the air snorkel leading to the MAF, leading of course to the throttle body, the purpose of the mass airflow sensor is to very accurately detect the amount of air that is coming into the engine. And there are a couple designs where it uses to do this, but the main point is to determine the weight of the air over a given amount of time. And this is why on your scan tool, if you have one, and we will cover ways of testing the sensor without a scan tool, with a scan tool, and also using another way without a scan tool. In order to measure the weight of the air, one thing to keep in mind before I describe how it operates is that the weight of the air is going to vary depending on its temperature. Colder air is denser than warmer air, so the MAF is going to be in direct communication with your intake air temperature sensor. And knowing the temperature and knowing the volume of the air coming in, the PCM is able to very accurately calculate the mass of air coming in over a given time. Of course, that calculation is the primary calculation used to estimate the amount of fuel delivery to get that 14.7 to 1 ratio. And then in conjunction with some of the other sensors to do a little bit of correction, and then mostly the oxygen sensor to do a final correction or trim. This system works very, very accurately at maintaining that stoichiometric ratio. Now, it goes without saying, if the intake air temperature sensor is inaccurate, the readings from your MAF will be inaccurate. Not that the MAF itself is inaccurate, but the extrapolation of that calculation for weight over time would be inaccurate. So again, another example of what I call the potential for a referenced code, or where if the IAT is grossly misunderestimating temperature, then the MAF sensor could get blamed by the PCM when it determines the air-fuel mixture is wrong. So very important to put everything together, as you see. Now let's go ahead and talk about the different types of MAF sensors. Back in the day, which by that I mean probably like the 80s, I remember even having an old truck that had this type of system. It was a very simple mechanical type sensor. They no longer use this. Any mass airflow sensor used now is going to be electronic, but it was what was known as a vane sensor. And the vane sensor just very simply had a little door or something here that was pushed against. Obviously, the more air coming in, the more this door would be pushed back. And there was a, what kind of device do you think would be on this door to measure its movement. We've covered this many times before. It would be a potentiometer. So being a potentiometer, it's going to have 3 wires coming off it, most likely. Back in those days, I didn't know a difference between a starter and a crankshaft, so maybe it didn't. But typically, you would expect, of course, a signal wire. You would have a 5-volt reference wire, and of course, you would have a ground. So you would have 3 wires coming off, and of course, the variable resistance would help determine airflow. Terrible system. One of the most common things that would happen is this hinge would get gummed up. You've seen the inside of a throttle body, I'm sure. If you are watching this channel as an advanced do-it-yourselfer, you've certainly done stuff with a throttle body. Very bad design, obviously, because of carbon buildup. Very inaccurate. So it is no longer used, and now they use electronic versions. So I'm familiar with, I can think of 3 other versions, and there certainly may be more. One of them is the hot wire, which I'm also going to include with the hot wire / cold wire. Another one is called a, I don't remember, but it's like a vortex sensor or something. It basically measures disturbance in the air. Of course, as the throttle opens to let more air in, there is some type of device in here that measures by frequency an air disturbance. We'll talk about that in just a little bit. Mostly we're going to talk about the hot wire, though, because that's the most common. And then there is also a hot film MAF that I've heard about recently. Not quite sure what that is, but I won't see one of those vehicles, I'm sure, for some time. I'm usually 5 or 6 years behind the technology before I see a car come in, because I don't see a car that's on warranty being a do-it-yourselfer, obviously. So let's talk about some of those other sensors. The hot wire we're going to go into much more detail, but let me look up what that one other sensor is, because it is definitely used in some cars. Okay, and sorry for that. It's called a vortex sensor. I may have even said the word vortex earlier, didn't I? But what it is basically a little item in here, and then there's a sensor. This item in here causes a disruption of the airflow, and that disruption is sensed by this vortex sensor to measure a frequency, and we will talk about this. This frequency measure for your do-it-yourselfer is going to be a pain in the dick. And then, of course, we've got the one that most of you guys are actually fairly familiar with, I'm sure. That is going to be the hot wire. And because this is so common, we're going to go into more detail. I know I kind of dismissed the vortex sensor. Sorry. I imagine maybe this is used more in Europe or something. But it doesn't matter, because whichever one of these methods you use, you will either be getting an analog or a digital signal from them. And a digital signal is going to be measured in frequency. The vortex sensor will be a digital signal. The hot wire can be one or the other. Some hot wires are analog, some are digital. Obviously, you can see we got an issue here. We are now going to have to understand the difference between an analog and digital signal, because the testing methods, especially for a do-it-yourselfer without fancy equipment, is going to be extremely different and actually very limiting. In fact, on a digital signal, without the proper equipment, you actually will not be able to do diagnosis on a MAF sensor, and we will understand why in just a little bit. But first, let's talk about the theory of operation of the MAF sensor, because that is going to be equivalent, and then we'll discuss the different outputs that you will be dealing with when you try to make a diagnosis or an interpretation of data from one in a diagnosis. Okay, so let's go ahead and discuss hot wire MAF theory of operation. So basically the idea with this, I don't know where people come up with these ideas, but this seems a little convoluted, but it is how it works. The PCM is going to control the temperature of this wire and hold this wire at a constant temperature. And from what I've read when I studied about this in, by the way, Service Manual is the source for most of my information on this. And different service manuals have said that this temperature is vastly different things. The GM service manual there, I believe, said that it was 100 degrees above ambient temp. How would it know the ambient temp, by the way? Intake air temperature sensor coming together. Some sensors also have another wire here called a cold wire used to make a comparison as well. But other references that I saw said that it was as high as 200 degrees over ambient temperature. Whatever the case is, it really doesn't matter. That part's not important. What is important is that the computer is going to maintain a constant temperature above ambient, whatever that is, and it's going to do it by either increasing or decreasing the current through that wire. Now, it should be pretty obvious by looking at this that if this throttle opens, more air comes in, what do you think is going to happen to the temperature of that wire? If you don't clearly see that the temperature on that wire would drop because you've never had the experience of blowing on something to cool it down in your life, you are on the wrong channel. Obviously, the more air that comes in, the cooler that wire would get, and more amperage would have to be delivered by the PCM in order to bring it up to the temperature. That change, or delta, in the amperage, which is also controlled, of course, by voltage, that change tells the PCM through an algorithm how much air must be coming past there. And of course, in conjunction with input from the IAT, it is able to estimate the mass of the air coming in that must have created that cooling effect. Conversely, close the throttle off, greatly reduce the amount of air, and now we are going to have changes to lower the amperage to put less current through the wire, bring that temperature back to that constant temperature it wants to maintain. That reduction tells the PCM there is less air entering the engine. It calculates accordingly and reduces the injector pulse length accordingly, so that any changes, we get a maintenance of that stoichiometric ratio regardless of the airflow. So regardless of the system, whether it's the hot wire, whether it's the vortex sensor, whatever it is, the output to the PCM is going to be, as I said, in one of two methods. It is either going to be a frequency output or it is going to be an analog output. So let's talk about the differences that we would see with these two different outputs, how we would identify them and test them. So the analog system is the one that most of you guys are very familiar with, especially if you're kind of an old timer. That was typically what everything used. And an analog system, basically you are going to see a change. The delta symbol or triangle is a mathematical expression for change. I use it a lot. And that is going to be a change in the voltage. You will be able to see that change in voltage quite easily using a standard digital volt ohm meter, like you guys, if you watch this channel, should be well familiar with how to use. And that is going to be done because of the simple operation of the sensor. There are going to be 3 wires on this sensor, sometimes 4. Those wires will be, first and foremost, a 12 volt supply to actually power that wire. It's going to be a, whoops. The second one is, of course, going to be a ground. And your third wire is going to be your 5 volt reference wire. And some will have actually 4 wires on it. And the 4th wire, I believe, maybe uses a different ground for the reference than it does for the 12 volt. Not exactly sure about that, but on a GM, you're going to definitely see 3. I'm much more familiar with GMs than most other cars. Now, keep in mind, and this gets off track just a bit, some cars, and actually on one of the cars that we're going to test on purpose for this reason I'm bringing this up, you will have considerably more than 3 or 4 wires. You may have up to 6 wires. If you have on your MAF sensor 6 wires, or more than 4 for sure, then what you have is sort of an integration of your MAF sensor with the IAT. And on newer cars, I see this more and more and more and more. So the IAT and the MAF are integrated into one unit. And I purposely, my Subaru has this design. I don't know whether it's a frequency or an analog sensor, but I know that it's going to have that. And the idea is I'm going to show you how we can differentiate which of the wires are for the MAF and which are for the IAT. But anyway, obviously it goes without saying that just like a, what else does this look like, by the way, for most of you guys? Pretty much like a potentiometer in many ways. Obviously, we're going to see a change in voltage relative between the reference wire and the ground wire as a result of the more or less air coming in. So it's going to look a lot in this model with your analog model like testing a throttle position sensor. It's going to look absolutely identical. You're going to have 0 volts at a rest position. Basically at idle, it's going to be very close to 0 volts. And then as more air comes in, there will be an increase in voltage up to 5 volts. So the more voltage that we read if we probe the ground and the reference wire, the more airflow that we are measuring coming through the sensor. And it should be very proportionate. If we move the throttle full open, we should get pretty much close to 5 volts. And at half open, we should get more around 2.5 volts. Again, very, very similar to doing a throttle position sensor. And you can, it is not the optimal way of doing it by any means, but you can use your traditional DVOM like many of you guys rely on. And of course, I rely on as well. But also on a scan tool, and we'll show all of this when we actually play on the car. On a scan tool, you will see usually that voltage reading available. You also will, on a scan tool, see the grams per second data available. And of course, if it is a digital sensor, you would see a Hertz signal available. So let's talk about the Hertz signal, and more importantly, why it literally hurts if you do not have the right equipment to test it. Now, your digital MAF is going to be indistinguishable from your analog MAF because it is going to have exactly the same wire pattern, either 3 or 4 wires, depending whether 1 or 2 grounds are used. You will have a signal wire, the power wire, and of course, the ground. And the difference is instead of a change in voltage that is sent to the PCM, there is going to be a change in frequency of the signal. And for many of you guys, you're probably turning this right off because you don't want to learn about this. I was that way too at one time, but it's actually pretty simple. So as we know from the analog, if we graph it, we will see a 0 to 5 volt change. So as more or less air comes in as a result of changing the throttle, or incidentally, by the way, the idle air control, incidentally, we would see a reflection in voltage accordingly, and most everybody is well familiar with that. In a digital signal, instead of it being a continuous sort of constant application of electricity that is sort of changed by changes in voltage, changes in resistance, it is going to be either a very simple on or off signal. And this would be on your 5 volt reference. So basically, this will be, if we graph it, either 5 volts or no volts. 5 volts or no volts. And there is no in between. It is on or off. If we get more air coming into the mass airflow sensor, then this signal is going to change and it is going to get faster. And that is going to be what we call a change in frequency. So let's describe this in a little more detail. So as we can see, we are either turning on or off at a very, very rapid rate, mind you, the signal from the MAF signal wire here. And the thing is that we need to understand some definitions about this digital trace. The first one is we see that this signal is actually repeating over and over. It is the same signal repeating over and over and over again. And basically the amount of these repeats within 1 second is going to be the frequency measured in hertz. So a hertz is the repeats of signal per second. So in this example, if this was a 1 second time frame, starting from the same repeat point, we would have 1, 2, 3 repeats of the signal. So this signal here is a 3 hertz. That would be an extremely slow signal by any standards in an automotive application. Typically with a MAF sensor, we're going to see 2,000 to 5,000 hertz. I've read somewhere maybe as much as tens of thousands even, and that is going to present a major problem with our voltmeter, and I'll show you why. So if by chance a guy named Kenneth comes up to you and asks what's the frequency, you can tell him. Now the thing is that remembering our MAF sensor, as more airflow comes in, what did I say? We're going to change the frequency. We will increase the frequency of this signal. So if we get more airflow into the MAF sensor, that signal is going to change. And it is going to get tighter. So that within 1 second, so now we can see that the frequency has doubled. It's now 6 cycles per second. So the frequency of 6 hertz is proportionate to the fact that we clearly doubled the amount of airflow from before. Now, the thing is that in this example, it's 6 hertz. In reality, it would be more like this. This change would be more along the lines of, say, 2,000 hertz, increasing to 6,000 hertz. So that's going to be a lot of these waves here, an awful lot very close together, that then when it increases, it's going to look almost just like a bunch of lines. And the problem is you need a very, very high speed device to measure this, even from the baseline of 2,000 hertz, because otherwise it's just all going to look like a bunch of lines. Each one of those lines, however, being the square wave. And square wave, of course, being the description of the digital signal because of the square pattern of on or off. Herein lies the problem with your digital volt ohm meter, because on top of understanding all the components in the car and on top of understanding this electricity, and there's a lot more with these square waves, we could cover things like duty cycle, pulse width, all this stuff, which we won't go into, maybe in another video, but you know, that's really not my realm. But if necessary, we'll go into this a little more. The problem is you also now have to understand how your DVOM works and the theory of operation with it. See, that's why auto mechanics, though it is not my career, it is a career, because you have a lot to learn on this. It is not just putting a code reader onto a car and then going to AutoZone and buying the part that the code reader said. As you can see, to really become an advanced diagnostician, it requires a hell of a lot of study. And I've been doing this for what, like 7 years now. The problem with this thing is, if you remember, even though this looks pretty simple, you have to remember that this is happening thousands of times per second. This on-off signal is very, very fast. And a voltmeter is not. It is not nearly fast enough to keep up with this trace. So for example, on an analog, if we were to manually turn a TPS, or if we were to step on the throttle pedal to slowly change our voltage and increase it, and then let off to decrease it, this is, fast enough that we can do that. If we use this on something faster, such as an O2 sensor trace, Pretty much, I'm sure all of you guys have attempted to use a DVOM on an O2 sensor trace. Does it go from point 1 to point 2 to point 3 to point 4 to point 5 to point 6 to point 7 to point 8 and down and up? No, of course not. It's going to give you readings all over the place. It's going to start reading like point 4 and point 82 and point 16 and point 454 and down the line. It's going to be a very choppy signal. Why? Because on a moving trace like this, the DVOM is just not fast enough. Plus, it's trying to take an average from the few readings it does take. So when you take these averages here, you get a very choppy response. That's on an O2 sensor signal. Can you imagine on something that's about 1,000 times faster? You can't do it. And there's another problem. And that is on your analog signal, you're going to have degrees of difference. So in other words, if this is a 0 to 5 volt, there is actually a 2.5 volt signal here. There is actually a 3.7 volt here. But on the digital sensor, it is either 5 volt or 0 volt. There is actually no in between. So that's a problem, because since your DVOM is trying to take an average of your signals, even on a somewhat faster moving analog, if it takes an average, say, of this 3.7 and 2.5, and it gives you somewhere around 3 on here, and then it reads, again, it's a little bit slower, but it reads up here, and maybe you've got a 4 and up here a 5. So your next reading that jumps up onto your screen is now 4.5. You get to see at least that there was some increase at that point. You're not going to see that on a digital signal, because your slow meter is going to be taking readings only every so often. Actually it would be, remember, there's thousands of these. So let's have reading here, and then way down the line we get another reading up here. The problem is when it averages your readings, it is going to show 2.5 volts. It is not going to show 0 and 5, 0 and 5, 0 and 5. That is for sure. It's going to show 2.5 volts. But the problem is that is going to be irrelevant to the frequency, because even if we increase the frequency, we are still going to have the same problem. The voltmeter, and there's going to be a lot more cycles between measurements now, but it's still going to do the same thing, and it's going to average out, even with the higher frequency, to show 2.5 volts. So when you have a change in frequency in a digital MAF sensor, you will not see a change in your DVOM. Do you think, if you did not understand that it could cause you to falsely diagnose a MAF sensor as being non-responsive? So some fancy DVOMs will of course have a frequency function on it. I do not own one that does, obviously. But for this type of sensor, you are stuck. You're going to either have to have a scan tool or an oscilloscope in order to do this type of reading. So I'll tell you what, let's do this. Let's take a break and go to the car and apply these concepts of the basic fundamental understanding to solidify our foundation. And then after we do that and verify all this works, we'll come back and we'll talk about problems you can have with the MAF sensor and how to diagnose all the possible problems that you might have.